Hello friends. So we were looking at the definition of exergy in the previous class. We said that exergy is defined as the maximum reversible work that can be extracted from an object or a system by running a reversible engine between the system and the surroundings until such time that the system comes to thermal and mechanical equilibrium with the surroundings. That is, its temperature and pressure get reduced to T0 and P0, thus reducing the system to what we call as the dead state. So the system comes to equilibrium with the Exergy reference environment by spending all its energy that it has in excess of the dead state, and we run a Carnot engine or a reversible engine using that energy in order to convert it into work output. So you get the maximum amount of work output that can be obtained. Then that quantity of work output is called the exergy of the system. Okay, right now we have defined it for a closed system where there is no mass flowing in or flowing out. So the exergy of a closed system came to be defined as, if E is the energy that is contained in the system, which is U plus potential energy plus kinetic energy with reference to the environment, then this can be the exergy for that quantity can be defined as E minus U naught, where U naught is the internal energy or actually the total energy of the system when it goes to equilibrium with the reference environment. So all the potential energy and kinetic energy it had have been converted to work, and the internal energy also came from U to U naught, and that difference also got converted into work. Right? So that is that part. And from that you discount the quantity that is not permitted by second law, which is minus T0 into S minus S naught, and you also discount the path by which the boundary is just pushed without any resistance from the external pressure. So against P0 the boundary is pushed. So there is P0 into V minus V0 which gets removed from this work, and T0 into S minus S naught which gets removed from this work. Then you get the definition of exergy. Okay, so let's go to the whiteboard to look at that expression. Right. So E minus U naught, which is the amount of energy that was contained in the system, which is the the internal energy, the potential energy, and the kinetic energy. Let's say that we converted this entire kinetic energy and potential energy into work, because they are 100% convertible into work, and this U minus U naught also got converted into work with a discount of T0 into S minus S naught, which part the second law does not permit you to convert heat into work 100%. So that part gets removed, and this P0 into V minus V0 is basically nothing but the displacement of the boundary from V to V0 against the dead state pressure P0. Okay. Whatever was done in with respect to an excess of pressure over P0 was delivered as useful work, but P0 into V minus V0 is not constituting useful work. So that's the basic premise. So we can interpret this expression as so much of energy that was available in the closed system has been reversibly converted to work, net of the quantity that is not permitted by second law to be converted to work, so that much is removed, and net of also the boundary displacement against the dead state pressure, okay, or the environmental pressure. So this is the definition of exergy of a closed system. So if I have state 1 and a state 2, okay, an object then moves from state 1 to state 2, then the maximum work that can be produced by this change of state from 1 to 2 would be equal to phi 2 minus phi 1, because if I take this as state 1 and let's say this as state 2 and this as, let us say, state 0, then this constitutes phi 1 and this constitutes phi 2, that is the amount of work that can be extracted by going from 1 to 0 and from 2 to 0. So from 1 to 2, then the difference is phi1 minus phi2, or phi2 minus phi1. So the okay, so the maximum possible work that can be obtained from process from 1 to 2 is actually phi2 minus phi1 minus phi2, which will basically be the difference in exergy between state 1 and state 2, or the change in exergy phi2 minus phi1 can be written in this form from here. It will basically be the u naught will get cancelled between the two, so it will be actually E2 minus E1. Okay, and this V naught will again get cancelled, so it will become plus P naught into V2 minus V1. Okay, and minus T naught, and the S naught will again get cancelled. It will be S2 minus S1. So this will be the change in exergy. So phi1 minus phi2 will be the maximum work that can be obtained by going from state 1 to state 2. So that is the expression that we would get. Now, if I try to evaluate this from the first and second law expressions for a closed system, we get another interesting insight into the process of energy conversion. Let's try to look at that. So suppose I write the first law for the change of state from state 1 to state 2. So you will look at a process going from state 1 to state 2. Okay. So the first law for this process will basically say E2 minus E1 is equal to the delta Q in plus delta W on. Okay, so this is the first law integrated from state 1 to state 2. Sorry. Okay, and the second law for the same process will basically say S2 minus S1 is equal to integral from 1 to 2 of delta Q in by TB plus sigma 1 2. Okay, so if I integrate delta sigma from state 1 to state 2, it's sigma 1 2. Now, if I substitute these two expressions into this phi2 minus phi1, which is the change in exergy between the two states, that will be equal to E2 minus E1, okay, plus P naught into V2 minus V1 minus T naught into S2 minus S1. Now substitute for S2 minus S1 and E2 minus E1 from here, then you get delta Q in from 1 to 2, okay, plus delta W on integrated from 1 to 2, okay, and plus P naught into V2 minus V1 minus T naught times S2 minus S1 will actually give you integral from 1 to 2 of delta Q in by TB, okay, plus T naught, so this also minus minus T naught into sigma 1 2. Okay. Now, if I combine these two terms together, I get an integral from 1 to 2 of delta Q in multiplied by 1 minus T naught by TB. Okay, because this is delta Q in into 1 and this is delta Q in into T naught by TB. Since T naught is a constant, I can take it in. So this TB is also constant. So this is the term that I would get. Plus, you get if I look at the work done by the object, I'll write it in terms of negative. So I'll write it as a minus delta W by minus. So delta W by integrated from 1 to, let me write it as W by from state 1 to state 2, okay, which is with a negative sign because W on is positive, so W by is negative, okay. And in the same, this one I will write minus, so minus of minus is plus, P naught into V2 minus V1, okay, and now minus T naught into sigma 1, 2. So now this is the same as this quantity, phi 2 minus phi 1, which is this. So I can say that the change in exergy from state 1 to state 2 has happened by three paths or three routes. One is through heat transfer, the other is through work transfer, and the third is through irreversibility. Okay, so the change in exergy from state 1 to state 2 has happened through heat transfer, the delta Q in, discounted by a quantity called 1 minus T naught by Tb. So suppose we say that Tb is higher than T naught, the boundary temperature is higher, which basically means that the object is at a higher temperature than the surroundings. Then this T naught by Tb is less than 1, so this whole quantity is a quantity less than 1. So the heat actually seems to run a Carnot engine between the boundary temperature and the surrounding temperature and takes the efficiency there, and that efficiency multiplied by dq in. So the energy that comes in from the surroundings to the object, a fraction of it is converted into work and added to the object. So that is the change that happens here. So this change is a positive quantity when this is positive, that is when Tb is greater than T naught. Okay. Let's look at the same case. So when the object is warmer than the surroundings, then the work done by the object removes exergy, so the exergy decreases because of that. Or if the work is done on the object, then this becomes a plus W on, which is a positive quantity, so it gets added to the object. So which is another thing that we can understand. When the object is at a temperature or energy level higher than the surroundings, if work is done on it, its exergy increases. So it's going away from the dead state condition. Okay, and whatever work we get as output, W by, is discounted by this quantity of boundary displacement due to against the dead state pressure. Okay, so that is the work transfer component, and this is the irreversibility component. So T naught multiplied by sigma 1, 2 is the amount of work potential that is destroyed irreversibly because of this entropy generation component sigma 1, 2. Okay, so T naught into sigma 1, 2 is basically the destruction of exergy. So this is exergy transfer or exergy exergy transfer during the process due to heat transfer. This is the exergy transfer during the process due to work transfer, and this is the destruction of exergy due to irreversibility. So these three constituents contribute to the change in exergy from state 1 to state 2, which is basically defined like this. The same thing is rewritten in this form. So you can actually say that E2 minus E1 plus P naught into V2 minus V1 minus T naught into S2 minus S1 is equal to integral of delta Q in into 1 minus T naught by Tb and W by minus P naught into V2 minus V1 and minus T naught sigma 1. If I consider a system which is colder than the surroundings, so the boundary temperature is lower than the ambient temperature, so then this quantity T naught by Tb is actually greater than 1, so 1 minus this would be negative because T naught is higher than Tb, so this is a negative quantity. So this delta Q in will actually contribute to a negative quantity of this one, so the exergy would actually decrease. Okay, so it basically means that the object is now coming closer to the dead state. So when the object is colder, a heat transfer into the object will actually contribute a movement of the object closer to the dead state, and therefore the exergy change is negative. And in the same fashion, now this minus W by, if work is being done by an object which is colder, then its energy goes further down, so it goes away from the dead state. So okay, this is negative. So the exergy change is, in this case, if the work is done by the object, there is then the loss of energy. So minus of that will be positive, and therefore it will move closer. But if there is a work on, then the object moves. So if there is work on, then it moves closer to the system, and if the work is done by, then it moves away from the dead state. Okay, and this one always destroys exergy, and therefore decreases the available potential to do work. So this is the way you interpret and understand the change in exergy due to heat transfer, work transfer, and irreversibility. Now, the last part of our discussion on exergy will basically be on flow exergy. So we, just like we did for open systems, the first law and second law expressions for open systems, if we try to define the exergy transfer accompanying a flow process, then what we will do, I am not going to go into the details of that. I would allow you to study it by yourself. So every time there is an inflow of mass m dot in from any inlet I, m dot I from any inlet I, then it will be accompanied by the work, flow work, which is Pi Vi, net of the quantity P naught Vi. Okay, so this is something for you to derive. So at all inflows, there will be a summation over I of m dot I into Pi Vi minus P naught Vi, and similarly at all outlets you will have a summation over exits of m dot E into Pe Vi minus P naught Vi. Okay, so these quantities get added to the m dot I phi I, which is the if I write phi as the capital Phi as the exergy, the extensive quantity, then phi per unit mass is written as phi. Just distinguish these two symbols. I write it with a capital Phi here. The lines on the top and bottom signify that. So the phi by m is small phi. So if I write phi I, so m dot I phi I, the exergy coming in with the flow that's coming in. M dot E phi E will be the exergy going out with the flow that's going out. In addition, because of flow work, there will be these two components that will get added. So these four terms will get added to the exergy transfer equation, and therefore we will be able to write the exergy transfer expression for a flow process as d phi of an open system by dt, just like you write for the first law and second law, the rate form of this expression. This would be summation. Okay, in the closed system also you had this q dot j, where j is a segment of a boundary, multiplied by 1 minus t naught by tj. So suppose I have an object whose boundary can be divided into multiple segments like this. Okay, so this is j is equal to 1, 2, 3, etc. up to, let's say, m. Then in each of these segments, let us say the temperatures are T1, T2, say Tj or Tj for segment J and Tm for segment M. Okay, so then at every boundary, if there is also a heat coming in, let's say Q dot in or Q dot J is the energy that's coming in that segment, then Q dot J into 1 minus T naught by Tj is the Exergy inflow accompanying heat transfer. Then you also add minus W dot by the object or the open system minus P naught into dV by dt. Okay, so this is the Exergy change accompanying work transfer minus T naught into sigma dot, which is the Exergy destruction accompanying irreversibility. In addition to this, you would have a plus m dot I multiplied by, there will be a psi I minus m dot E multiplied by psi E, which is basically derived from the phi I, phi E and the flow Exergy components. So with the effect where psi is getting defined as H minus H naught, okay, minus T naught into S minus S naught. So this is all the lowercase letters. This psi is the flow Exergy at any inlet and outlet. So this is psi I. It will be Hi minus H naught minus T naught into Si minus S naught and so on. So this quantity psi I and psi E are called the flow Exergies, which will be used in these two expressions, just like you used enthalpies in these expressions when you used internal energy here in the first law statement. So now this can be looked upon as a statement of balance of Exergy. So the rate of change of Exergy of an open system would be equal to the sum of the rate of change of Exergy due to heat transfer minus the rate of change of Exergy due to work transfer minus rate of decrease in intro Exergy because of irreversibility plus the rate of inflow of flow Exergy minus the rate of outflow of flow Exergy, where this flow Exergy basically has the U minus U naught, the P naught into V minus V naught component has already gone in here, minus T naught into S minus S naught, added with this part of it, the m dot, the PV minus P naught V naught. So U minus PV and sorry U plus PV minus U naught plus P naught V naught becomes H minus H naught. So that is basically what you get in this term, H minus H naught minus T naught into S minus S naught. So that is the term that comes in the flow Exergy component. So it actually has the flow energy component, just like you had the flow energy component in the case of your first law for open systems. Okay, so this is an equation for Exergy balance, and from this again you can say that it's actually quantity, which is this is an equation which is very similar to your bank balance analogy equations that you wrote, conservation equations that you wrote for the case of mass conservation, energy conservation. But also there is a clear similarity. In the case of second law, there was a non-conserved term which is in the form of generation of entropy. Entropy is produced due to irreversibility. Here there is a Exergy destruction due to irreversibility. So this is Exergy inflow due to heat transfer. This is the Exergy outflow due to work transfer out. This is the Exergy destruction. This is the Exergy inflow due to mass coming in, and this is the Exergy outflow due to mass going out. So this basically gives you, and this can be, if there are multiple inputs and outputs, this will be a summation over I, and this will be a summation over E, and that makes the equation more general. Now here what we can do is to again write these expressions simplified for steady state steady flow and uniform state uniform flow. For steady state steady flow, you can write d by dt of phi OS is equal to 0. Okay, with the result that you will get m dot in psi in. Okay, the in is without the n there. M dot I psi I, which is the quantity that is coming in, plus q dot multiplied by 1 minus t by t naught, qj dot tj by t naught, summation over all q's, all the j's. Okay, so this is the exergy transfer due to heat transfer coming in. Okay, this would be equal to, or if you can also write the exergy destruction here and the expenditure, so then it will be minus w dot by minus p naught into v minus v naught. So this is the exergy transfer due to work transfer minus T naught S gen or sigma dot. This would be equal to m dot E psi E. Okay, so this would be your expression for steady state steady flow. Maybe these two negative quantities can be moved to the other side if you would like to retain these two quantities here, which is inflow and heat transferring flow on one side, and the work output and the exergy destruction moved to the other side to keep them positive. So you can keep it that way, but this is your steady state steady flow expression. And for uniform state uniform flow, of course, you change it from phi 2 minus phi 1, so you get an expression which is very similar to the phi 2 minus phi 1 expression that we wrote here, except that you would have additional terms for psi in and psi out terms integrated over time. Okay, so that is the additional thing that you would have. So there we will stop the case of this one, and you can actually look at the textbook by Moran and Shapiro. I deliberately followed the textbook of Moran and Shapiro reasonably verbatim in the whole chapter, so that by reading that and by looking at the worked examples there, you will be able to understand the concept of exergy substantially well. So please do that, and we can have a doubt clearing session for understanding the difficulties that you might get in this. Okay. So you read the chapter on exergy. Okay, so with that we'll close for this lecture and continue in the next lecture.